Hi all, this is Dr. K. Raghuram Mohan Reddy, Associate Professor, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. Right, the course name is Unconventional Machining Process. The topic is Electrochemical Machining Problems and Solutions. Okay, right. At the end of this session, student will be able to solve the problems on material removal rate of electrochemical machining. This is the course learning outcome of the topic. Okay, so however, student can solve any kind of problem because here material removal rate is the main parameter to be calculated, but sometimes material removal rate may be given and we need to find some other parameters. Okay, right. However, before we discuss the various problems associated to this, let us discuss the total non-traditional machining processes and its classification. Okay, so non-traditional machining processes have classified mainly into mechanical, thermal, chemical and electrochemical. Okay, so under mechanical, ultrasonic machining, water jet machining, abrasive water jet machining, ice jet machining. Okay, under thermal, electro discharge machining, electron beam machining, laser beam machining, ion beam machining, plasma beam machining. And in chemical and electrochemical, chemical machining, photochemical machining, electrochemical machining. Okay, right. Now let us discuss electrochemical machining process. Okay, right. An ECM, electrochemical machining process. Okay, so material removal rate calculation. Okay, in the first problem, material removal rate. Okay, so an ECM process is used to machine a steel workpiece. The process operates at a current of 1000 amperes and the material has an equivalent mass of 55 gram per mole. The valency of the material is 2. Calculate the material removal rate in gram per minute. Okay, right. Here current is given I 1000 amperes and equivalent mass is given 55 gram per mole and valency is given 2. Okay, and Faraday's constant F is given 96500 C by mole and MRR, material removal rate formula, that is I into E by N into F. Okay, simply substitute the values, given values. Okay, so here I is given, E is given, N is given, F is given. Okay, so substitute the values so that you get this one. Okay, right. Voltage calculation. Okay, right. In an ECM process, the inter-electrode gap is 0.5 millimeters and the specific resistance of the electrolyte is 2 into 10 power minus 2 meter. The current flowing is 1500 amperes and the total over voltage is 2 volts. Okay, now calculate the applied voltage. Right. Now inter-electrode gap is given 0.5 millimeters, so we need to convert it to meters, and the specific resistance the electrolyte is this one, 2 into 10 power minus 2 ohm meters. Next, the current flowing, current is given 1500 amperes. and the total over voltage is 2 volts. Okay, over voltage VO is 2 volts. Okay, now calculate the applied voltage. So in order to find the applied voltage, first we have to find the resistance R. Okay, so that is this one. Okay, but VR equal to IR. Okay, already we have known this. Okay, but however, voltage dropped due to resistance VR equal to I and this one. Okay, where I equal to 1 square meter. Okay, assume unit cross sectional area for simplicity. Okay, sometimes we have to assume these things. And finally, VR equal to 1500 into this value. Okay, 2 into 10 power minus 2 into this gap 0.5 into 10 power minus 3 by I. Okay, so we get, sorry, 1 not I, we get 0.015 V. Okay, right. So applied voltage equal to VR plus VO. Okay, so what is VR? VO is given and VR we have calculated. Okay, so to calculate VR, first we have to find the IR. Okay, that is nothing but VR. Okay, so I is given. What is R? Rho into D by A. Okay, so that is given resistance. Okay, 2 into 10 power minus 2. Okay, and D is 0.5 into 10 power minus 3. Okay, by A, assuming 1 square meter. Okay, so that we get VR. Once if we get VR, simply add VO. Okay, over voltage. So finally we'll get 2.015 volts. Okay, right. Next, surface finish calculation. An ECM process operates with a feed rate of 0.1 mm per minute and the electrolyte conductivity is 0.15 seconds per centimeters. Okay, if the gap between the tool and the workpiece is 0.3 millimeters, calculate the surface finish RA in microns using a simple model where RA equal to feed rate into gap by conductivity. Okay, so here everything is given in this problem. Okay, so here feed rate F is given 0.1 mm per minute. Okay, and conductivity K is given, small k, that is 0.15 S by cm. Okay, next gap 0.3 mm is given. Okay, and surface finish RA formula is that F into G by K. Okay, F is given, G is given, K is given. Simply substitute the values to find the, okay, here in this problem it is given, okay, F into gap by conductivity. Okay, so nothing is there to find anything. Okay, so substitute the values, so finally we get 2 microns. Okay, electrolyte flow rate calculation. Okay, so in an ECM process, the electrolyte flow rate is critical for removing the dissolved metal ions. The current is 500 amperes and the electrolyte velocity is 2 meters per second through a 0.02 square meters cross sectional area calculate the volumetric flow rate in cubic meter per second. Okay, right. So here current I is given. Okay, 500 amperes. Suppose if it is given in milliamperes, we need to convert into amperes. So we have to multiply with 1000. Okay, and electrolyte velocity is given 2 meters per second. Okay, and cross sectional area is given. Okay, how much? 0.02 square meters. Calculate the volumetric flow rate. Okay, so we have the total discharge formula is that Q equal to VA. That means electrolyte velocity into cross sectional area. Okay, so here current is given. Let us see, is it useful or not? Okay, in the problem, some data may be useful or may not be useful. Okay, right. Here Q equal to V into A. What is V? 2. What is A? 0.02. So 0.04 cubic meters per second. Okay, right. So in this problem, this current is not useful, whether it is in amperes or milliamperes. Here, particularly in this problem, this is not useful. So student has to understand the given data. Okay, right. Next, tool wear rate calculation. Right. In an ECM process, the tool wear rate is negligible, but for a particular tool, the wear is measured as 0.02 grams after 200 minutes of operation. Okay, calculate the tool wear rate in gram per minute. Okay, right. What is the given data here? Tool wear, that is given 0.02 grams. Okay, and the time of operation is given 200 minutes. Okay, now calculate the tool wear rate in gram per minute. So that is very simple. Total wear by time, so that we will get gram per minute. Okay, so 0.02 by 200. That's what here. W by T. Tool wear by time. Okay, so that we will get gram per minute. 0.0001 gram per minute. Okay, so here tool is also subjecting to wear, but the thing is that per minute it is 0.0001 gram. Okay, so it is very small value. Okay, next, problem number 6, electrochemical equivalent calculation. Okay, right. Calculate the electrochemical equivalent Z in gram per C for a material with an atomic weight of 63.5 gram per mole and a valence of 1. Okay, now atomic weight, that is M, 63.5 gram per mole is given. Okay, and valency N equal to 1 is given. Okay, now Faraday's constant F, 96500. Okay, so student has to remember or bring back to mind this Faraday's constant F. Okay, right. Electrochemical equivalent Z equal to M by NF. Okay, so here this value is to be bring back to mind by the student, otherwise cannot solve the problem. Okay, so that we will get this value. Okay, Right. Let me reiterate all these things uh, at a glance. Okay. Right. Let me summarize here. In the first problem, we need to find the material removal rate. Okay. So here current is given, I is given. Okay. And equivalent mass is given, capital E. Okay. And valency small n is given, and Faraday's constant F, that we have to make a note. Okay, here Faraday's constant to be taken. Okay, now MRR, material removal rate, formula is that current I into equivalent mass E by valency into Faraday's constant. Okay, so with this we can find the material removal rate. Okay, right. In problem number 2, see here, over voltage is given. Okay, we need to find voltage drop due to resistance VR. Okay, so applied voltage equal to VR plus VO. Okay, so VO is given. We need to find VR in this problem. Okay, so in order to find VR, we have to, V means I into R. Okay, am I correct or not? I means current, R means resistance. Okay, but here in order to find that resistance, okay, we are simplifying rho into d by A. V equal to VR plus V naught. However, VO is given. In order to find VR, again I into, in place of R, we have to arrange this rho into d by A. Okay, so very simple. So once if we get that VR, okay, so just V equal to VR plus VO. Okay, so with this the problem 2 has been finished. Okay, now here in this problem, directly in this problem, in order to find RA, feed rate into gap by conductivity, so F into G by K, that is given. So nothing to worry. Again in this we have to find the Q. Okay, so here current is given, and student may think somewhere we have to keep that current. Okay, but here that is not required. So velocity into area. Okay, so that we'll get the flow rate. Next, in this problem, tool wear is given. Okay, and time of operation is given. So calculate the tool wear rate. So simply tool wear by time. Okay, next, electrochemical equivalent calculation. So for this, the student will have to bring back to mind the Faraday's constant, that is F, that is 96500. Okay, so here Z equal to, calculate the electrochemical equivalent Z. Okay, that Z equal to M by N F, where N equal to valence and F equal to Faraday's constant, M equal to atomic weight, that is given. Okay, so with this, let us conclude. These are the references associated to this topic. Okay, thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.